In this section, we are going to talk about artificial neural network models. Auto-Keras can optimize the hyperparameters that go into generating artificial neural networks for us. These hyperparameters are crucial for good performance on a given problem, and they usually take a long time and a lot of knowledge to be properly determined. In this video, we are going to talk about ANN generation. Auto-Keras can generate artificial neural networks for various tasks by optimizing their hyperparameters. We've already seen image classifier at work, which tries a lot of neural network candidates for a given task. We did not go into detail on what kind of candidates it tries. In order to do that, we would have to go quite deep into Auto-Keras' source code. And this is not very important for the scope of this course. All we need to know is that it attempts to generate a proper and efficient classifier. Here, we will focus on its multilayer perceptron abilities. A multilayer perceptron looks kind of like this. You might be familiar with this from your basic machine learning knowledge. We have an input layer, a number of hidden layers, and an output layer. Each hidden layer has a certain number of hidden units, or neurons. It also has an activation function. So we've already mentioned three hyperparameters: the number of hidden layers, the number of hidden units, and the activation functions. Auto-Keras can determine the best ones for us by itself. As you know, these networks can learn many things. Here is one for the exclusive OR function. So two inputs corresponding to 2 bits, and the output will be the first bit, exclusive OR the second bit. We have one single hidden layer with 2 hidden units that compute simple functions. We also have an activation function which is given here. S of x is 0 if x is lower than 0, and 1 if x is larger than or equal to 0. This is called the logistic function. So let's take a few examples. So we're given 0 and 0, and we'll have to output 0 for this, because 0 XOR 0 is 0. So if we plug in the values here, 2 times 0 plus 2 times 0, s of minus 1 is equal to 0. So this hidden unit will output 0. And this hidden unit will output 1, because the result of this computation will be 3, and s of 3 is 1. And if we plug in 0 for x1 here and 1 for x2, we get 2 times 0 plus 2 times 1, which is 2, minus 3, which is minus 1, and s of minus 1 is 0, and this is correct. 0 XOR 0 is 0. Let's take another one, 1 and 0. So we get 2 times 1, which is 2, plus 2 times 0, which is 0, so 2, minus 1, which is 1. So 1 here. And similarly, we get minus 2, minus 0, plus 3, which is 1. So this will also output 1 here. And for both of these, we get 4 minus 3, which is 1, and s of 1 is 1, so the output will be 1. This is correct. 1 XOR 0 is indeed 1. For the other examples, we won't be doing the computations, but you can do them for yourself. So for 1 and 1, the hidden units will output 1 and 0, and the result will be 0, which is correct. 1 XOR 1 is 0. For 0 and 1, the hidden units will output 1 and 1, and the result will be 1, because it was 1 here as well. So you can see that it can be quite difficult to come up with these values for the hidden units. In fact, if you try to train such a network from scratch, you will see that it's not exactly trivial to implement. You can spend a lot of time tweaking and debugging your code, and Auto-Keras can make this much simpler.